All right, things to remember. Don't use too much solvent. If you, what you want to use is a minimum amount of solvent, and then you can add about 5% excess solvent to prevent crystals from forming too early. Okay, so you need to pay attention and record what amount of solvent you add to just get your crystals to dissolve. That way you can calculate that 5% excess off of that volume. Sometimes you may have colored impurities. Whether you do or not for this lab, you will be doing a decolorizing step so that you can learn it. If you have colored impurities, we use activated or decolorizing carbon to remove any of these impurities. Basically, this activated carbon has a high surface area that absorbs dissolved organic solvents, which is great if your organic, or rather it absorbs dissolved organic substances. It's great if your substances are colored. However, that increased surface area can also adsorb your product. So you don't want to use too much decolorized carbon or expose your product to it for too long. You will see some loss if you expose your product too long to the decolorizing carbon, or if you add just way too much of the activated carbon. When you are using the activated carbon after you've added it to your boiling solution, then you use gravity filtration to separate the solution from the insoluble carbon. So in the gravity filtration, you're trapping the impurities that you don't want, i.e. the insoluble carbon, and the material that you do want, the solubilized acetanilide, will move through. Whenever you use this gravity filtration setup for a recrystallization or in the recrystallization process, you want to heat this setup in order to avoid early crystallization. If your glassware is at room temperature, then your crystals of acetanilide are likely to form on that cooler glassware since it's in a boiling hot solution. Your lab book takes you through how to heat that setup, and I have that covered as well when we get to the procedure steps of our pre-lab lecture. Typically you only do your decolorizing step if you have insoluble impurities or carbon in your solution. Actually, that point is for the gravity filtration. You're only doing that if you are trying to collect something that you do not want moving forward, okay? Because as we'll discuss later, there's a good chance for several errors with this gravity filtration process. When we're doing the gravity filtration, we're going to use fluted filter paper. The purpose of fluted filter paper, it increases the surface area inside a funnel, which consequently speeds up the filtering, okay? We don't want any crystals to form, if at all possible, inside of the funnel, because of course they would be trapped and separated from the material you're using going forward. So you want to have the solution move through as fast as possible. Okay, figure 3 on the slide shows you what the fluted filter paper will look like in your glass funnel. You do want to use the powder funnel for this. You don't want to use the long stem funnel because that's a lot of glass in the long stems, especially some of the ones that y'all have in your drawers, and it just increases the chances of early crystals forming as well as clogging if the crystals form in a large amount. And it makes for a very messy process for this gravity filtration. So use a shorter stem funnel. Note that the fluted filter paper doesn't sit all the way up against the glass funnel. You want to make sure that you only pour into the filter paper, don't pour above it or on the outsides of it. But it doesn't sit the way that your perhaps traditional folded filter paper from Gen Chem does. Figure 4 is showing you how to fold a fluted filter paper, and traditionally Harold has an example sitting out in the lab, and we'll see what he has done with COVID, but generally he provides an example of what that looks like. I'll also look for videos to post online showing you how to correctly fold fluted filter paper. Effectively, you're kind of making like a fan type situation with the filter paper to give a lot of creases and increase the surface area. All right, once you have filtered, if it was necessary, which again, for this lab, we'll be doing it so that you learn the process, but it's not always necessary. But after filtering, Then you let your solution cool to room temperature slowly, okay? You get that nice lattice structure forming and bigger crystals if you let the process happen slowly. Once your solution has cooled to room temperature, then you will further chill it in an ice bath. Usually you let it sit in an ice bath for 5 to 10 minutes to form as many crystals as possible. Remember, since solubility decreases as the temperature decreases, the colder your solution gets, the more crystals should be forming. Okay, so again, remembering those solubility rules comes in handy, especially if you don't quite remember what to do, say in a month when we're doing another lab that requires a recrystallization. If you remember solubility rules, you can usually feel your way through the process. Sometimes crystals don't form at room temperature. If that's the case, there's some things that we can do. All hope is not lost. The first thing that I would tell you, if you said, hey, crystals didn't form and I've been sitting here for 10 minutes, well, I'm going to have you scratch the bottom of the flask with a glass stirring rod. That's going to create a nucleation site for the product crystals to form and start forming and creating those lattices. You need to really scratch the bottom of the flask when I tell you to do this, not just kind of gently scraping, but feeling like nails on a chalkboard scratching so that you create a good nucleation site. The other thing that you can sometimes do, but that we can't do for this lab, is if you have a pure sample of your material, you can drop a small crystal in to serve as a seed crystal, as we call it, which will also act as a nucleation site. More often than not, in the organic lab, we're either purifying something or we're making something that we do not have in our stockroom. So scratching the bottom of the flask is what we typically do in order to encourage crystals to form. Finally, after we have our crystals formed, we use vacuum filtration to isolate crystals from the liquid that they form from. The liquid they form from is called the mother liquor. You'll see this referred to many times throughout your lab book. When I've got an image of the vacuum filtration on the next slide, but make sure that your glassware that you're taking with you to the vacuum filtration setup is very clean, okay? You don't want to introduce new impurities into your crystals just because you didn't double check and clean your glassware, or the person that used it before you didn't clean it well. You'll be using a disc of filter paper, so it will be a much smaller piece of filter paper than what you used for the fluted filter paper. And once you put the disc of filter paper in your Buchner funnel, you'll wet it with recrystallizing solvent to keep it in place so that it doesn't shift and expose any of the holes in the Buchner funnel bottom. You will then kind of suspend the crystals in solvent. Sometimes you can do this simply by swirling your flask. Other times you might need to take your glass stirring rod or a spatula to kind of help scratch or scrape up some of the crystals and get them suspended within the liquid. You'll turn on the vacuum and then carefully pour the solution onto the filter paper so that you create kind of an even layer of crystals so that they can dry effectively, okay? Once you have poured the solution out, traditionally we'll wash with pure chilled recrystallized solvent. So that's something to remember as you're preparing for the vacuum filtration. You need to make sure that you're chilling some recrystallization solvent. And then finally, you'll ideally let your crystals dry on the vacuum. We'll discuss that a little bit more. Things to remember after your vacuum filtration: make sure to take your glassware and your Buchner funnel back to your bench with you. So many times students will forget to take their glassware, and then the next time they need to do a recrystallization, they don't have the glassware or the funnel in their drawers to do it. Like I said, figure 5 in your lab book shows you the vacuum filtration apparatus. This week, we will actually be using the mother liquor to rinse our crystals. We'll use it to rinse our crystals 3 times, and then we'll still use the final rinse is always used with pure recrystallization solvent. We want to use that recrystallization solvent chilled so that you're not dissolving any of your crystals that are already collected on the filter paper, okay? Your filter flask will be this one, the one on the left in the setup. And of course, you also have a Buchner funnel that has a stopper that you checked out a couple weeks ago. Typically, we keep our vacuum filtrations in hoods. We'll have to assess where they ended up once we have kind of rearranged for COVID. But the trap that we see here and the vacuum tubing line is actually hooked up to a small vacuum pump. Those are kind of community setup, and we have 4 to 5 of those, or maybe 3 to 5 of those in our lab. So the idea of the trap is, in case you're not paying close attention and you let solvent drain all the way through the Buechner funnel up to that side arm that is connected to the trap, then you have the trap that will get the liquid in it, as opposed to if this hose was directly connected to the vacuum, you would be putting liquid directly into your vacuum. It would start sucking it off, which would of course ruin the vacuum. Once you have finished your filtration process, you need to break the vacuum before you disassemble it. And our traps are designed basically the same way they are in this image. We have a piece of tubing here on a straight glass tubing piece, and it has a little clamp. Ours isn't a screw clamp, it's actually a pressure clamp. You'll just be able to kind of open that up, and you'll hear a change in the pitch of the vacuum. And that breaks the vacuum so that you don't potentially get any backflow from the trap back into the filter flask. In a vacuum filtration apparatus, you want to keep what's in the funnel. You do not want to keep what's in the filter flask. Okay. However, sometimes crystals go through the pores in your filter, which is why for this particular lab, we'll be using the mother liquor to rinse out the Erlenmeyer flask for the first 3 rinses. All right, you're almost done. You've gone through the process of recrystallization. You collected your crystals in your Buechner funnel on your filter paper. You need to let the crystals dry. The lab book tells you to leave it on the pump for about 10 minutes. Well, if we only have 3 or 4 pumps for 20 people, we can't do that. So what we traditionally do, if we have a recrystallization step, we let the crystals dry in our drawers over the week, okay? And then the next week we come in and we get our final mass, our dried final masses. That way we can calculate the percent recovery. And we see the percent recovery equation from our lab book here. It's equal to the mass of the recrystallized compound divided by the mass of the crude compound. And then of course you multiply by 100% to get it into a percentage. So this is what I was talking about when I said make sure to collect your data. Write down what your exact mass was of your crude compound. Yes, the lab book tells you a certain amount, but if you weigh a little bit above or a little bit below that, you can get a very different percent recovery if your denominator is not correct versus your final mass of the recrystallized compound. The last thing that we'll do once the crystals are dried and you've obtained your final mass, you will assess the purity of your compound by taking a melting point of the purified material as well as the crude starting material. We don't always have this luxury, but since this is a technique lab, we do. And you'll kind of compare the 2 melting points, and hopefully you remember what things you should see differently between the purified material melting point and melting range, as we could say as a hint, versus the crude material melting point / range. Also, for good observations and things to discuss within your lab report, do a visual check. Make sure describe what your crystals look like. If your material is supposed to be white, which remember, we can always figure out what something should look like if we look at the safety data sheet for that material, or a simple Google search, and Wikipedia usually gives you this information accurately as well. Of course, it's always referenced in order for us to believe it. But if your material is supposed to be white, but it's off-white in color, you need to go back through the decolorizing process and the recrystallization process. One big thing that we sometimes see is a slight gray tinge to crystals after this lab, and you can tell that when they're wet, so you wouldn't have to wait until the next week. If you have gray tinge, that means some of your activated carbon came through. Maybe you accidentally poked a hole in your fluted filter paper, and that's why you're seeing some of that you've actually introduced more impurities into your material as opposed to purifying it.